Hi everybody, today we're going to talk about power functions and polynomial functions. So let's start with the definition of a power function. A power function is a function that can be written in the form f of x equals k times x to the n. Here k and n are just real numbers, so remember we call k the coefficient and n will just be the power. I want you to really pay attention to the fact that f of x is a monomial, so there's no other terms, just one singular term for a power function. So let's take a look at a few examples to decide which is not a power function. So I have A, f of x is 5x cubed. I have B, g of x is 9 over x. I have C, h of x is x squared plus 5. I have D, y is the cube root of x. And E, capital F of x, is 4 to the power x. So let's go through one by one. I want to remind you, we're looking for something that looks like f of x is k x to the n. So our first one looks great. F of x is 5x cubed. That would be a power function. 9 over x, we could write as 9x to the negative 1. So that still fits our format that we want to have. So that's a power function. C, where h of x is x squared plus 5, this is a problem. This is not a monomial. This is a binomial. So this would not be a power function. D, y is the cube root of x. Well, I can write that as x to the 1/3 power. So I get it back as an exponent, and that says that is a power function. And then the last one says 4 to the x. Now, this is not a power function because the base is a constant instead of the base being the variable. So 2 cases where we don't have a power function. So let's grow this definition a little bit and move on to a polynomial function. A polynomial function can be written in the form f of x is a sub n x to the n plus a sub n minus 1 x to the n minus 1 plus a sub n minus 2 x to the n minus 2 plus dot 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 a sub 1 x to the 1 plus a naught. This time the n's are integers, so they're not real numbers, and all of these integers are going to be greater than or equal to 0. The a's can be different. They're all real numbers. We just need the a sub n not to be 0. A sub n x to the n is called the leading term, and it's going to be really important for us. A sub n is going to be the leading coefficient, and then n is going to be the degree of the polynomial altogether. So you will find we spend a lot of time just talking about this first term, a sub n x to the n, and we'll get to the other terms in other videos. So let's decide if these functions are polynomial functions. If they are, we're going to give the degree. If they're not, we're going to say why not. A says f of x is 4x to the 5th minus 7x squared minus 12x plus 25. So this is a polynomial function. The degree would be 5. So it's just the power for the leading term. When you're doing this, make sure you look through all of the terms. It's not necessarily going to be the first one. Nothing says we have to write the polynomial in descending order. So just make sure that you're taking a good look through it before you decide what the degree is. B says g of x is 8x to the 4th minus 2x to the negative 3 plus 12. So what do you think about that? Do you think that's a polynomial? Hopefully you said no. And the reason would be that this negative 3 is not an integer, so I can't have negative exponents. C says h of x is 1/5 x cubed minus 6 times x to the 1.2 plus 9x minus 5. Look at this one. Look at the exponents. What do you think about them? I hope you think that no, this is not a polynomial because 1.2 is not an integer. And then our last one says f of x is 6. Now, there's nothing else there, but that's okay. This is a polynomial. What I want you to think about is this could be 6x to the 0, so our power or our degree of the polynomial would be 0. So constants are polynomial functions, they're just degree 0. So we're going to spend a lot of time talking about end behavior. When we look at the end behavior of a function, we are really just concerned about what's going to happen as x goes to positive infinity or as x goes to negative infinity. So we're going to start by looking at a graph, and that will help us determine what we're looking at. So what we're saying first is when x is going to infinity, what's happening to my function? I want you to see as I'm going to the right, my function is going down. So as x gets bigger, f of x is getting smaller. That goes to negative infinity. On the left side, as x goes to negative infinity, so I'm on my graph and I'm following along, it's going up. So up is positive infinity, and I'm putting the plus sign to really reinforce the sign. Let's try that again. This time when I start on the right, so I'm on the graph and I'm headed toward infinity on the x, and look, I'm going up towards positive infinity for my f of x. Same thing, I'm going towards negative infinity, so I'm going to follow this graph, and I'm looking as I go smaller and smaller for my x's, I get a bigger and bigger function value, so that is also going to positive infinity. So sometimes the right and the left are doing the same thing. These are both going up. Last time, the right was going down and the left was going up, so they don't have to do the same thing, but they might. So now we're going to mix power functions and polynomial functions, and what I want to say is the power function of a polynomial, like a sub n x to the n plus a sub n minus 1 x to the n minus 1 plus a1 x1 plus a naught, is a sub n x to the n. So what I'm doing is I'm taking this entire polynomial function and I'm just grabbing the leading term. The end behavior of f of x is going to be the same as the end behavior of the polynomial's power function. So I won't have to worry about all the little details in the function. I just grab the leading term. So let's talk about end behavior, and let's just start on the right. So taking this polynomial function, a sub n x to the n plus a sub n minus 1 x to the n minus 1, etc. When I look at the leading term and really just looking at the leading coefficient, when the leading coefficient is positive, the function is going to go to infinity on the right. If the leading coefficient is negative, then the function is going to go down on the right. So just whatever's in front, say I had f of x equals 3x to the fourth. 3 being positive says when x goes to infinity, f of x goes to infinity. But if I change that and I just make it f of x is negative 3x to the fourth, now when x goes to infinity, f of x will go to negative infinity. So the right side is completely determined by the sign of the leading coefficient. The left side is determined by the power of the polynomial. And really more specifically than that, it's determined by whether the power is even or odd. So if the power of the polynomial is even, the end behaviors are going to match. So whatever it does on the right, it'll do on the left. If the power is odd, well then that's going to be opposite. So whatever it does on the right, it will do the opposite on the left. I said, think about things like x squared, because we should know x squared by now. So here's x squared, power is 2, and the right and the left match. Then I said, well, think about x cubed, which looks like this. It's odd, and see the right and the left are opposite. So I kind of like having something that I can go back to that I'm very familiar with. That way, if I get confused or I think, what was that rule? I can say, okay, well, I know what x squared is, evens match. I can write down x cubed, that's odd, odds are opposite. So I think evens match, odds are opposite. That really helps me. So let's try that. Let's do some examples. First thing we want to say is the only thing I am looking at is 5x to the 7th. 5 is positive, so let's write that. This is positive, which means it's going to go up on the right. So on the right side, it's going to infinity. 7 is odd. Odds are opposite. So the opposite of infinity is negative infinity. Notice there's no calculation here. You're just having to put together the rules and just think through how things are connected. So let's try again. I have f of x is negative 3x to the fourth plus 8x cubed plus 6x. I'm only looking at the negative 3x to the fourth. It's starting as negative. Negative goes down. So f of x goes to negative infinity when x goes to infinity. The power is even. Evens match. Match says they're the same. So negative infinity on the right, negative infinity on the left. The next one says I have f of x is negative 9x cubed plus 2x squared plus 10x plus 3. So I want you to think about, what does the negative 9 tell me? Am I going to go to infinity or negative infinity? Hopefully you think negative is negative, so you're going to write negative infinity. Then I want you to look at the 3. Think 3 is odd. Odds are opposite, which means the opposite of negative infinity is positive infinity. On the next one, we're just going to add a new piece in. We're going to find the end behavior, and we're also going to talk about the intercepts. So I have x plus 2 times x minus 5 times x plus 3 squared. Now, I don't have this written out. This is in factored form, so I need to think about the powers. So this is power 1. Here's another power 1. And then this one is power 2, so I want to add that up. 1 plus 2 says this is overall power 4. X is positive, X is positive, X is positive. That says overall A sub n is positive. So positive says it's going to go up on the right, and then being an even power says it's going to match and also go up on the left. To get the x-intercept, we're just going to take each of these factors and set them equal to 0. So x plus 2 is 0, x minus 5 is 0, x plus 3 squared is 0. So the first one, I get a negative 2, then I get a positive 5, and then I get a negative 3. The power doesn't matter. If you took the square root of both sides, you would have x plus 3 is equal to 0, so you can ignore this power and just find your 0. So I have 3 intercepts. I'm going to write them from smallest to largest, so I'm going to write negative 3, negative 2, positive 5. The y-intercept, which I said could be called the f-intercept, comes from plugging in 0 into the function. So I would have 0 plus 2, I would have 0 minus 5, and I have 0 plus 3 squared. This is 2 times negative 5 times 9, which is negative 90. So I have 3 x-intercepts, and I can never have more than one y. Same thing for this one. I said find the end behavior of f of x is x times x minus 4 times x plus 1 cubed. So power 1, power 1, power 3. 1 plus 1 plus 3 is power 5. X is positive, x is positive, x is positive. So that says it's going up on the right. 5 is odd, which means that's going to be opposite, which will go to negative infinity. If I do the x-intercepts, again, I have 3. I have x is 0, x minus 4 is 0, x plus 1 cubed is 0. This gives me 0, 4, and negative 1. Again, if I write them in order, smallest to largest, I have negative 1, 0, and 4 as my x-intercepts. The y-intercept comes from plugging in f of 0. So I have 0, 0 minus 4, 0 plus 1 cubed, which that one's easy. That one's just 0 this time. Multiplying by 0 gets rid of all the others. In this one, we are going to again find the intercepts and the end behavior. So let's start with the end behavior. It'll be easier. Seeing that 4 is positive says when x goes to infinity, f of x will also go to infinity. Because 5 is odd, when x goes to negative infinity, I think odds are opposite, so it's going to go to negative infinity. To get the x-intercepts, I'm going to take 4x to the 5th plus 12x to the 4th plus 8x cubed and set it equal to 0. Very lucky. All of the terms are divisible by 4. All of the terms I could divide by x cubed. So when I divide that out, I get x squared. I get 3x plus 2. Keep the 4x cubed. Then I can factor x cubed plus 3x plus 2 into x plus 1 times x plus 2. So I have 3 zeros. I have 0, I have negative 1, and I have negative 2. Then to get the y-intercept, or they might call it the f-intercept, we're going to plug in 0. So I have 4 times 0 to the 5th, plus 12 times 0 to the 4th, plus 8 times 0 cubed, which is just 0. So as we continue to talk about zeros, we also want to add in something called turning points. So back to our polynomial function, a sub n x to the n plus a sub n minus 1, x to the n minus 1, plus a1 x to the 1 plus a naught, where we had our integer exponents that are greater than or equal to 0. We want to say 2 important things here. First, the polynomial will have at most n real zeros. Keep that in mind. The degree of the polynomial tells us how many zeros we're expecting, and we're going to get into that more. For today, the power tells me the highest number of zeros I can have. And then n minus 1 will be the number of turning points. Now let me show you what a turning point is. A turning point is a point where the graph changes direction. So if I'm looking at this particular one, I can see it was going down, and at this point 0, 0, it goes up. So this 0, 0 would be a turning point. Same thing over here. This function is going down, and then it changes and goes up, and then it changes and goes down. So I can see there was 1, 2 turning points, 1, 2 turning points, and this one only had 1. What we want to remember here is f of x equals a sub n x to the n. As our leading term, we will have n minus 1 turning points. So there's this connection between the number of turning points and the degree of the polynomial. So look at this graph. It goes up, it goes down, it goes up. So I have 1, 2 turning points, 2 turning points. Means that the degree of this polynomial is at least 3. So the smallest it could be is 3. So 2 plus 1 is 3 is the smallest it could be. So you're going to take the turning points if you're looking at a graph and just add 1 to it. So take a look at this graph. Can you tell how many turning points it has? I see 1, and then I see 2, and then I see 3. So I think I went down, I went up, there's a turning point. I went up, I went down, there's a turning point, down, went up, there's another one. So 1, 2, 3. You're going to add 1, which is 4. 4 is the minimal number of turning points I can have. As you're looking at this, sometimes it could be tricky. So you want to make sure that the degree you come up with matches with the end behavior. What do I mean by that? This end behavior, they're both going up. So it says this has to be an even degreed polynomial, and I got 4. The last one has opposite end behavior, so I know it has to have an odd degree, and I got 3. So just in case you get something weird where it doesn't match, think about how you might need to adjust it to answer the question. So let's take that away from a picture and just look at a polynomial written out. We're going to find the degree, the leading coefficient, and the maximum number of real zeros of the polynomial, and we'll just add on how many turning points it could have. So I have f of x is 12 minus 2x cubed plus 7x squared minus 3x plus 8x to the 4th. Now again, remember how I talked about? Go through and look. I have power 3, I have power 2, I have power 1, I have power 4. 4 is the highest power, so this 8x to the 4th is my leading term, and 8 is the leading coefficient. The power of the polynomial being 4, so 4 will be the maximum number of real zeros, and we can have at most 3 turning points. So there's a lot we covered today. But the good news is we will continue to use it. So the more times I use it, the better it's going to get. And repetition really is important to how we learn things in general. So be patient with yourself. Try homework. Try practicing this. And I think you'll find the more times we do this in the next week or two, it's really going to sink in.